welcome to the course. So, this is about the tool wear and tool life. So, the tool wear, normally if you see the tool wear, it describes the gradual failure of the cutting tool due to regular machining, because it is a progressive wear basically. So, it describes gradually how atom by atom or molecule by molecule or the amount gradually it will goes off. That is what the progressive tool wear is. Just if you see to the introduction to the progressive tool wear, there is another tool wear that is called catastrophic tool wear, which I am not discussing, but catastrophic tool wear is normally sudden breakage. So, that will happen basically in the brittle and ceramic materials, but the gradual tool wear or the progressive tool wear takes place in the other materials like HSS, carbide tools and all those things. Okay. So, here we are seeing about the crater wear and the flank wear. These are the two varieties of the progressive tool wear that one can see here. At the same time, how to represent schematically, if you see the schematical representation, this is the rake surface and this is the flank surface. So, the wear that is taking place on the flank is a flank wear, and the rake surface, the wear is taking place is crater wear. Okay. So, now the crater wear represents normally in terms of crater wear depth. This is crater wear depth, you can see the in terms of crater wear depth, and in terms of flank wear it is normally represented in the flank wear land. This is the flank wear land. So, on the flank face. Okay. So, these are the two wears commonly observed in the tool wear in the machining processes. Okay. There are other wears like notch wear, edge wear, many other wears are there, but since this is the introductory course to the machining process, so we are concentrating mostly on the two wears, that is crater wear and then the flank wear. Okay. This is the progressive wear. Now, you can see how it takes place on the machining process. You have seen previously. So, now you see this is a cutting tool. Basically, in this cutting tool, because of the chip motion, you can see this is the crater depth that takes place. Because of the workpiece interaction, normally abrasion, there comes the flank wear. This is called the flank wear. Normally, it represents in terms of flank wear land. This is represent in terms of flank wear land. That means indirectly what it means is it is a width of the flank wear, and in terms of crater wear it represent in terms of crater wear depth. Okay. So, this is about, and if you want pictorially you can see in the next slide. So, this is the crater wear depth. Normally, this is the crater wear which takes place on the rake surface. And this is the flank wear. So, I just talk about your flank wear. Okay. So, that is the thing, but this is the flank wear land. Or flank wear width. Okay. The other term is width. This is the practically what we observe in the machining process. If you want to represent it schematically, the flank wear represent like this and crater wear represents like this. Okay. The other view that you can see is the crater wear. This is the other view. Okay. So, one noting point that you have to always see here is, just I will come to some question here which I will explain you from the point of questions. Just you have to see what is, it starts slightly away from the cutting edge. That is what you have to observe. Okay. So, I will ask you one question and I will also tell you the answer also. The basic mechanisms, there are three mechanisms are the causes by which the tool wear takes place in the machining. So, whenever we talk about the output, that is, if there is a research paper on the machining process, so people talk about different wears. Whenever you have a different wear, you should talk about the physics of it. What is the physics behind it and how this process is taking place, what are the basic mechanisms that are the people explained in the textbooks, That are the mechanisms that explained in the research papers and all those things. Okay. The first one is abrasion, the second one is adhesion and diffusion. Okay. So, just we see this abrasive wear. So, these are the three hard particles microscopic variations on the bottom surface. Okay. So, this is about the explanation. So, microscopic variation on the bottom surface of the chip, again this is normally there is two types of abrasions will takes place. One is a 3D and another one is a 2D. Practically speaking, it is a 3D. So, for better understanding, whenever we do the modeling or whenever we want to understand the things, some people understand it is a 2D. The adhesion, normally adhesion is nothing but the joining. Abrasion is nothing but it is like upbraiding the surface. Whenever a kabaddi player falls on a sand in the villages, you see the players. So, the sand, if it is here, so that will abrade the skin. That is nothing but the abrasion. And the adhesion normally is just joining, that is two materials of different materials. And diffusion is the starting point of adhesion, that means higher concentration to lower concentration. If the material transfer is gradually taking place, that is called the diffusion. Anyhow, I will come in detail about all these things, that the mechanical loss of material by micro cutting action. Normally, if you see, this is to explain you what is abrasion wear. We just taken the example of the micro cutting action. So, whenever you have a two body abrasion, that means that there are involvement of only two bodies. In our present scenario, these two bodies are, one is the workpiece material, another one is a tool material. Okay. So, if there is a interaction or a wear between two bodies, the abrasive wear between two bodies, then it is nothing but the two body abrasion or two body wear. In term, if you have a third body, normally for example, this is commonly two body abrasion is commonly in terms of machining process, where the tool, single point cutting tool is there and you are removing a material. Assume that you are machining a copper with respect to the one of the hard tools like HSS or carbide tools. Normally you will have two body abrasion. The three body abrasion will takes place when there is a third body comes into picture, like you can see this picture. So, where third body come into picture, which can rotate about its own axis. Okay. What I mean to say is, in for example, just to take a process where loose abrasive particles are used, so like lapping process. In a lapping process, you have a lower plate or a workpiece or something, an upper plate where you have a, or the lower one is there, upper one is there, one will be your workpiece, and you put a slurry and you just polish it. What will happen? You have the component, you have the lap on, and you have abrasive particles. Whenever you try to polish it, what will happen? The abrasive particles will also take part along with the lap. Okay. So, this is what the three body abrasion. Now, the same thing whenever we want to explain from the point of metal cutting. See, whenever you have a single point cutting tool where chip is taking place, if you are putting a cooling fluid, what will happen? Because the chip is high temperature, it will be in the form of semi solid or something, and the tool is also, chip is continuously flowing, because of which the tool gets hot and hot. Okay. So, in that circumstances, it may create some particles. Okay. This is in the semi solid state. Whenever the liquid with a high convective heat transfer coefficient falls, it may generate particles. There is a chance, I am not saying it is a compulsory. So, there is a chance whenever you are machining low melting point materials like aluminum and all those things. So, there may be the chance of particles formation because of the cutting fluid, maybe. Okay. So, not only the chip and tool interaction, here because of the foreign body particles, that is particles generated because of the interaction of the cutting fluid with the chip bottom side and the top side of the cutting, where the particles comes. Because of this, you have a chip, you have a tool material, in between you have particles. So, because of which the 3 body aberration also comes into the picture. Okay. So, normally if at all I want to check this 3 body aberration or something in terms of tribological aspects, people uses for the 2 body aberration, normally people uses workpiece material and tool material, and they will do the tribology, pin on disc and all those things. If they want to go for the 3 body aberration, basically on the disc, pin on disc, that is POD, they will, instead of disc, they will take the abrasive sheet and they will just perform the experiments, and they try to correlate various tribological issues. So, in that way this can be studied. Okay. So, the next one is adhesion wear. The mechanical wear process where particles generate from the softer and to contacting surface characterized metal surface, and mechanism is welding and rupture. Okay. So, basically whatever here welding and rupture is the tool wear mechanism. Okay. So, pertaining to the adhesion, only welding takes place. So, whenever you are machining certain material, when the temperature goes high, what will happen? There is a welding, that is nothing but the adhesion takes place between chip and the tool for a instant, okay, for a microsecond or a nanosecond. So, what will happen if I have a soft workpiece material whose chip is continuously flowing on the surface? In that circumstances, chip is carrying, already told that 80 to 85% of the generated heat. Okay. So, it tries to weld its internal layers nanometer by nanometer by nanometer on the tool surface, and after some time, because of this, because of the friction and high temperature of the chip, this temperature goes inside of the tool, and the thermal softening of the tool takes place, and at a certain point of time the tool top layers will goes off. That means that crater wear, whatever I am just shown, the crater wear takes place. That means that layer by layer of the beneath surface of the chip will accumulate, that is welding takes place, and because of this the temperature of the tool goes high. Even tool also gets 10 to 15% of the temperature, 80% of the chip is giving which is flowing also giving the temperature. Chip is a continuous body and the tool is a static body. In that circumstances, the thermal softening of the tool takes place after some time, and these top layers of the tool, whenever after some time it goes off. So, that is nothing but the rupture. So, this is about the adhesion and rupture. Okay. Soft body, normally workpiece will be there, soft body, and the harder body will be tool, I mean cutting tool. This is about the adhesion wear. Now, the diffusion wear. Normally, the diffusion's basic definition, if you speak, it is called higher concentration to the lower concentration. Okay. So, you can say whenever the chip is flowing on this and at high temperature, normally the machining temperature, gradual diffusion of atoms which are lying on a beneath of the chip gradually goes and sits on the tool surface. That means that it will go into the tool surface. That is nothing but the diffusion. What I personally feel is adhesion is a higher version of the diffusion. Okay, maybe just it's in my view. So, if the partial atoms of the workpiece chip is going to the lower concentration, that means that here in the chip it is a higher concentration of the workpiece material, the lower concentration is the tool material. So, if it goes, that is nothing but the diffusion. The chemical wear process, due to diffusion, atoms from one surface to the matrix of the other surface goes. The phenomena affect the physical properties such as hardness, toughness of the tool material and all this. Normally, diffusion is proportional to the temperature. At high temperature, the diffusion will be very high. Okay. So, the initial step of the adhesion may also can call as the diffusion process. Okay. The amount of material transfer is proportional to the time of the contact. Okay. So, amount of material transfer is proportional to the sliding speed. If the sliding speed is very high, the temperature also will be high. If the temperature is very high, so the diffusion will also takes place. If the contact area is very high or the contact surface between this very high, what will happen? This is the lower concentration and this is the higher concentration. If the contact area is this, it is different. If it is this, it is different. So, if the contact area is very high, normally it is proportional to the diffusion where is proportional, that means that it will increase. Okay. These are the three mechanisms. One is abrasion, where rubbing action will takes place, it is a mechanical action. The second one is adhesion, which is the thermal one, and the diffusion is also a thermal one. Okay. So, these are the three mechanisms on which the tool wear depends. Okay. Now, we will go into the two wears. So, the possible two wears in orthogonal metal cutting process are, one is crater wear, we have already seen, and the another one is the flank wear. So, this is also I have shown in the previous slides, which is crater wear and the flank wear. To show you the isometric view, just we have given you a glimpse here on a single point cutting tool. This is the crater wear and this is the flank wear. Okay. So, this is about the flank wear. Okay. So, normally flank wear, I already told you, flank wear width is the one, flank wear land is the one. Another wear is nothing but the notch wear. You can see the notch wear, which I am not going to talk much about this one. Just I am talking about the introduction to the tool wear. So, I talk about only two wears, but however, you can see at the end of the flank wear there is a wear called notch wear. So, that is another type of wear. So, there is another one where is nothing but the nose radius wear. You can see here on the nose radius. Okay. This is the nose radius and this is the sharpness radius, which is okay. So, these are the glimpse that schematically I can show you. Okay. So, the crater wear. So, the crater wear, if you see crater wear, this is the crater wear that I have already shown you. So, crater wear wears care on the rake surface of the tool, possible mechanisms. Now, we have to see what is the possible mechanisms. We have seen three mechanisms, that is abrasion, adhesion and diffusion, among which causes more in terms of crater wear, which is high in terms of flank wear. That means, which is the most responsible mechanism in the crater wear, which is the most responsible mechanism in the flank wear, that we have to see. Okay. See, the possible mechanism sequential order, I am just saying about the crater wear. The crater wear means, if my workpiece is there and the tool is there, if my chip is moving on top of it. Okay. So, the chip is carrying lot of temperature and it is imparting into the tool, that is what I have said, and the basic mechanism here is welding and rupture. Why I am saying is welding and rupture? If you see this picture where my chip is moving, so the bottom surface of the chip gradually welds on this surface of the workpiece, and when the thermal softening takes place, this will takes away. This particular portion goes off. That means that the basic mechanism, dominating mechanism here is adhesion and followed by abrasion, because it has a sticking zone as well as a sliding zone. Okay. So, the crater wear takes place in terms of sticking as well as sliding, but the sticking it is dominating and sliding is slightly less. So, sliding region is mainly because of the abrasion, and the diffusion also plays at very high speeds. Okay. The basic mechanism that one can tell is adhesion is the dominant mechanism of tool wear in terms of crater wear. Okay. So, if you see the crater wear, so normally crater wear represents in terms of this, these are the representations. One is the distance to the middle, that is Km, this is the Km. Another one is Kb, that is the width, this is the width of the crater wear. Depth of the crater wear, that is a Kt, which normally you can say is as crater wear depth. And KL is distance from the start. So, this is nothing but a KL from the starting point to the cutting edge starting point. Okay. These are the notations, and the abrasion area is this one. So, crater wear normally represent in terms of crater wear depth, that is what I mean to say is KT, crater wear depth, which is represent. Okay. Now, the question, assume that I am taking only 3 types of tools. One is 0 rectangle tool, positive rectangle tool, okay. First, let me take 2 where normally forces will be very high. Basically speaking, assume that here is, if it is F1, this is F2. So, F1 will be slightly higher than F2 because positive rectangle is there. Assume that there is a crater wear on a 0 rectangle tool. What will happen? This is my 0 rectangle tool. So, I have a crater wear. So, how it look like? It look like similar to my positive rectangle, where my forces is F3. From the visibility, from the what we are seeing, it should give F3, F1 should be greater than F2. Okay. So, normally it should be from the geometry, what is the visibility, from this point normally F1 should be greater than F3 also, okay, from the visibility point of view, but it is not so. But the case is F3 will be greater than F1, greater than F2. This will be the condition. Now, question is why? Okay. So, the question is simple. I have a 0 rectangle tool where the force for the same conditions, for the same depth of cut, speed, cutting speed and all those things, I have a 0 rectangle. This is 0 rectangle, this is positive rectangle, this is a wear, tool wear, that is crater wear takes place. Okay. So, in that circumstances F3 should be where tool normally will experience more forces compared to 0 rectangle, but geometry wise it looks like a positive rectangle. Now, the statements are contradictory. Basically, the person who is doing experiment will experience F3 greater than F1. Okay. From the visibility point of view, from this light, it should resemble like a positive rectangle. Okay. The answer, as per the partial answers, I can say is normally the tool wear won't starts from the cutting edge like the positive rectangle. Okay. So, it has a slightly distance will be there. Second thing, here it is a smooth cut. In a positive, if you see, it is a smooth cut. Here the tool wear is random and it is not proper. So, the chip that moves will have lot of disturbances and all those things. Okay. These are the partial reasons why normally F3, whatever we are seeing here, F3 is greater than F1, greater than F2. Okay. So, that is the some of the reasons. There are many other reasons also. For the same cutting tool, normally this starts slightly ahead, this is the distance and it is rough. Okay. So, other one is the flank wear. The wear scar on the flank face of the cutting tool, this is also progressive wear, but here the basic mechanism is abrasion. Okay. So, because the workpiece or the machined workpiece is in contact with the flank face. Okay. So, if you see the workpiece, normally the rubbing action takes place on the flank face of the tool. Rubbing action takes place here, because of which there is a flank wear land. Okay. The dominant mechanism is abrasion. So, that is a mechanical rubbing action against the cut surface, that is the machined surface. Flank wear represents the length of the flank wear land. Okay. See, this is nothing but the flank wear land. So, the summary is, in the crater wear, adhesion is the dominating mechanism, here abrasion is the dominating mechanism. That is the bottom line of the wear mechanisms versus the wears. Okay. So, now we will see the flank wear versus time, how the flank wear progressively increases with respect to time and all those things. Okay. So, if you see this one, the time of cutting versus the tool flank wear, normally two similar trend the crater wear also follows. So, I am just touching about only the flank wear. I will also explain you why I am touching only the flank wear, because the flank wear is the criteria that people can easily measure, but the main reason is the tool life criteria basically takes from the flank wear only. So, that is the main reason. Whenever that point comes, I will explain you. Okay. So, there are three regions. If you see in the tool wear region, one is the break-in period, initial break-in period. Then the second one is steady state wear region, that is a uniform wear rate, and the third one is a final failure region, that is the accelerated wear region. Okay. So, the first phase follows rapid wear, uniform wear followed by accelerated wear. So, these are the three wears in the three regions of break-in period and steady state wear region and the failure region. So, we will go by one, the region 1. Okay. So, the graph is divided into three distinct regions. As I said, it is a break-in period, steady state and as well as the failure region. So, the region 1, initial breakdown region. Okay. So, this is initial breakdown region. In this region, due to sudden breakage down of the sharp cutting edge, so the rapid initial wear takes place. Since the cutting edge is too sharp, normal load on the sharp edge is high and the wear occurs rapidly. That means, we have seen in the merchant circle and all those things where the cutting tool is too sharp, that means that sharpness radius is 0. Okay. So, sharpness radius is nothing but my rake surface is there, my flank surface is there, wherever this rake surface and the principal flank surface meets at the cutting edge, that is called the principal cutting edge. The radius of this one is nothing but the sharpness radius. Okay. So, normally the manufacturers try to keep it as sharp as possible. So, that sharpness is very good, that means that sharpness radius is too low, that means that it is too sharp. So, in that circumstances, whenever the load takes place, that means that whenever the machining process starts, this cutting edge is too sharp and after some time suddenly goes off, that means sharpness radius suddenly increases, that means that the sharp edge will goes off, that is nothing but initial breakdown region. Okay. So, that is why initially this portion will come. Okay. So, I said initially, because your area interacting with respect to the cutting region because of the sharp cutting edge is very less. So, that will goes off automatically after some time, that is called initial wear by breakdown or something. The second one is steady state wear region, where uniform wear rate takes place. Okay. In this region, after some time, the surface temperatures are sufficiently high, which causes the thermal softening of the tool. So, the normal pressure of the surface, soft surface is high and uniformly wear takes place. That means, whenever you have the sharp cutting edge is gone, now your sharpness radius is increased. So, the contact area between workpiece and the tool is very high. In that circumstances, the chip is going on by shearing action. So, temperature gradually increases in the tool because of the friction, because of the tool carrying temperature and all those things. So, thermal softening of the workpiece tool takes place. So, the normal pressures gradually increases and the wear gradually uniformly increases. Okay. This is the second region. If you see the third region, that is called rapid breakdown. When the tool wear exceeds its normal load high, the sudden fracture, that is called catastrophic failure occurs. This is nothing but the failure region. Okay. Okay. What is it's going to be take place is, so the thermal softening of the tool takes place gradually and the tool become soft and it loses its properties basically, which are the main important for machining operation. So, this all goes and suddenly there will be a fracture in the tool, because that is nothing but the catastrophic failure. Catastrophic means sudden. If you see these three regions normally, so initial breakdown, this is a summary where the initial region, that is a region 1 initial breakdown uniform, where the sharp edge will goes off immediately and the uniform temperature goes into the tool because of thermal softening takes place. So, uniform progressive tool wear takes place, and the third one is breakdown takes place because it is completely thermal softened, because the machining time is too high and that the tool is a stationary body. That is why the catastrophic failure takes place. This is about the time versus the tool wear. So, now we will go to the tool life. As I said, when I am explaining you that I am explaining you to the flank wear. Why I am explaining the flank wear? See, the similar mechanism is there in crater wear also. Just so you can go through that some basic textbook, so you can get it. And tool life, if I say which way it can be treated as a tool life criteria, okay, whether it is a flank wear or crater wear or why. Okay, that's I said you when I was discussing about flank wear mechanism and all those things. Okay, which way? So, can anybody guess? It's normally the flank wear. Okay. So, why the flank wear? Whenever the machining operation is taking place, crater wear takes place on the rake surface and the flank wear takes place on the flank surface, and the flank surface is the surface which will be in contact with my final product. So, whenever customer asks me, I have to give a product to him in a good size, good tolerance, good surface finish and all those things. If my flank wear is disturbed or the flank wear is high, in that circumstances I cannot give him the good product, because the product comes out will be in a not good shape or in an acceptable form for a customer. So, obviously, my chip will be in contact with the rake surface, which causes this wear, crater wear. Chip I do not bother, because the chip is the one which is not useful for me. I cannot say useful, but you can recycle into the workpiece material and all those things, but I am worried about the final product. If at all I want to give a good product, my flank wear land should be within the limits. If my flank wear is the criteria, if my flank wear I can keep the criteria as my criteria, I can give you good product. That is why always or the most of the time flank wear will be the criteria. Some of the times crater wear will also be criteria, that is whenever you are speaking about high speed machining and all those things where the temperatures are goes high, in that processes crater wear is also a criteria. But however, for the normal conditions of the machining process, the flank wear is the criteria that one can follow. So, the tool life. Tool life normally can be defined in many ways. You can see the length of the time that cutting tool can functional proper before it begins to fail. Okay. So, it is performing its own function, it is the machining operation. So, if it is fail, that means that I have to change my tool. That means that this is about my tool life. One way, the tool life criteria can be related to the blunting of the cutting edge due to unavoidable wearing process. Okay, blunting of the cutting tool. If my cutting edge is gone, what I mean to say is that I have to replace, because otherwise lot of vibrations will take place which hampers the accuracy of the product and all those things. The third one is the criteria of the tool failure in the virtue of wear length, which can easily measured. And then most crater wear is used in tool failure criteria. I said that in the high cutting speed, that is high speed machining basically. Okay. Normally here crater wear will be criteria. Okay. So, that is what I want to convey. Now, what are the variables that affects the tool life? If at all I want to see what are the variables that affect the tool life of my any tool that I have taken, whether it is a HSS or carbide or diamond or something. So, the variables affect is cutting conditions, tool geometry, tool materials, workpiece material, type of cutting fluid and cutting fluid application techniques. If you see some of the things, some are already given, that is cutting conditions, tool geometry, workpiece material and all those things. These are you can find in some of the textbooks. However, cutting fluid technique and cutting type of cutting fluid, these are all you may find in some of the new textbooks. Whenever we prepare our slides or our notes, normally we follow multiple textbooks. So, for the basics we follow the old books, and some of the pictures that whenever we take from our own research. Since we are doing some of the research in these areas, we also take it. That is why research and teaching goes hand in hand. Okay. So, whenever we teach, we also teach some of the advances that are found during the research. Okay. So, the first one which we can see is the cutting conditions. So, the cutting condition, the rate of wear and the cut is proportional to the cutting speed, that is Vt power n equal to constant. This is called Taylor to life equation. So, whenever you see this Taylor to life equation, Vt power n equal to constant, where the V is cutting speed, T is the tool life and n and C are the constants. Okay. So, V is the cutting speed, as I said, T is the tool life and n and C are parameters that depend on workpiece and tool material, that is nothing but workpiece material and tool material combination. N and C depends. Okay. It is not depend on either workpiece material or the tool material. It will always depend on the combination, whether you are using HSS versus steel, HSS versus cast iron or carbide versus cast iron or mild steel or something. Okay. Normally, the typical values for the tool materials, whenever you are machining the one of the workpiece materials like high speed steel, whenever you want to machine non-steel workpieces, it is n equal to 0.125, C equal to 120, okay, in terms of meters per minute. In steel workpieces 125 and 70, cemented carbide if you see 0.25, 900, steel workpieces 0.25 and 900, ceramics it will be, if you see the values of N and C are gradually increasing with respect to tool materials. Okay. The basic problem if you see in the Taylor to life equation is it is considering only cutting speed as the criteria, but if you see that is not the practically acceptable theorem. So, that is why there is a modified Taylor to life equation where it is incorporated with respect to depth of cut as well as feed. Okay. So, Vt power n equal to constant was a Taylor to life equation. Now, feed and depth of cut is incorporated and constant is there. So, n and C material constant, x and y also have similar material combination constant, where D is the depth of cut and feed. Okay. So, now it is practically acceptable. Okay. That means the tool life majorly depend on my cutting velocity and followed by feed, followed by depth of cut. Some of the research papers, they show this, that for the normal conditions of speed, depth of cut and feed, basically the contribution of the Taylor tool life equation or the tool life, cutting speed will contribute more, followed by the feed, followed by the depth of cut. In some circumstances, it may be like depth of cut also plays a major role compared to the feed. So, there is a striking balance between these two. Okay. So, if you see the time of cutting versus tool flank, the effect of normally I said this Vt power n equal to constant. If you see 3 cutting velocities, if okay, so one velocity is 100 meters per mm and 130 and 160. If you are going to increase the speed, the cutting time and for a less cutting time, the tool flank wear will increase. So, this shows that tool wear is proportional to your cutting velocity. Okay. If you are increasing to 160, if you see, this is the time of cutting. For 130, this is the, for 100, this much is your time. Okay. So, I mean to say is, if my speed is very high, that means my tool life is, or the time of cutting before it reaches to the 0.5, that is a criteria, 0.5 mm is a flank wear. Okay. So, let me explain a problem for some of the people who are beginners to the manufacturing and all those things. Just I will give you some. A tool run at 160 meters per minute lasts for 5 minutes. If the tool runs at 100 meters per minute, it lasts for 41 minutes. What is the C and N values? If you see this one, 2 conditions are given, that is, in one case V1 is given as well as T1 is given. Second case V2 is given and T2 is also given. Normally for this we are giving for a constant workpiece material and tool material. That means, if I am using a same material combination, my N value, my C value are same. Okay. So, considering that, you can solve like this, V1 T1 power n equal to constant, which is equal to V2 T2 power n. So, if you take log on both sides, you can easily get, and you can get the value, okay, of the n. If you get the n value, obviously if you can put into any one of the equations, you can calculate the C value. This is how you can calculate the material combination constant n as well as C. Okay. This is about the problem. So, whenever I am giving you these problems, so in the examination also you may get some of the simple problems where the question paper goes like multiple choice questions, where you may have to solve the question and you have to choose the answer in the ABCD. So, you should be prepared for the problems as well as the theory. Okay. But in my case, mostly it will be theory based. So, problems will be slightly less, since I am not touching much about the mechanics. As I said, some of the professor will take this course in this season or the next season, where he explains mostly about the mathematics. Okay. So, the second one is the tool geometry. You can see the tool geometry. So, the tool geometry, if you see, normally that in crater wear. So, in the crater wear, increasing the rake angle, cutting forces reduces, and cutting forces and the cutting temperature result increase tool life. Now, what I mean to say, if I increase the rake angle, my tool chip will be smoothly flows. At the same time, forces will reduce. If the forces reduce, that means that my crater wear will obviously goes down. When the tool rake angle is large, the cutting forces are lower and the tool edge is weakened, resulting increased the wear. Okay. So, you cannot go for increasing beyond certain level of my back rake angle. If I go on increase, assume that this is my Okay. Up to this is okay. I can increase by slightly. I cannot go like this. If it is go, then the material available to cut is very less. So it weakens the tool. That's why optimum rake angle will give the maximum tool life. Okay. You should choose the back rake angle or the rake angle optimum such a way that the tool life will be maximum. In the flank wear, increasing the flank angle reduces the rubbing action between the tool and the workpiece, hence it improves the tool life. This is the workpiece. This is the flank angle. Okay. This is the flank angle which helps from the rubbing action. If I give the 0 flank angle, what will happen? If I give 0 flank angle, it will completely rub against this one. So always you have to provide the flank angle so that rubbing won't takes place. Okay. High value of the flank angle also weakens the tool. Okay. So what I mean to say is, I can give a flank angle like this. If I start giving like this, what will happen? The material amount of material will be very less. So it weakens the tool material or the tool. So therefore, high feed rate, lower optimum value is maximum for the tool wheel. Okay. Normally you have to choose optimum flank angle. Higher feed rate, lower is the optimum value of the maximum tool life. Okay. So you should go, I mean to say, you should go for optimum flank angle also. This is about the flank angle as well as the rake angle, how this will affect. The third one is tool materials. Okay. So the tool materials, if you see the tool materials, selection of tool material. Okay. The selection of tool material, what are the important? One is hardness. That means that hardness of that particular tool material at elevated temperatures. Okay. If a machining process is taking place and the temperature that is generated is, assume that 700 degrees, 800 degrees, at that temperature it should possess its original properties. I mean to say properties pertaining to hardness. Assume that if it is not losing its hardness at elevated temperatures, that means that its hardness is good. Okay. The toughness is the impact forces to the tool. Normally toughness also should be provided to the tool. The toughest tool material normally is the HSS. Okay. So if you don't provide toughness, what will happen? The impact forces it cannot absorb. And all the wear resistance, normally wear resistant, it should be wear resistant, otherwise the tool wear will takes place very fastly. So chemical stability, it should be stable whenever the machining operation is going on. Okay. Otherwise it is a combination of tool material, workpiece material, some chemical, I mean to say the cutting fluid is falling and atmospheric environment is there where nitrogen is there, where the oxygen is there, and some of the other gases are also there, depend on the location of the industry and all those things. So it should be chemically stable also. Okay. You can see glimpse of the tool wears, some of the just practically what people have observed. So the wide variety of cutting tool materials used are, one is a high speed steel, uncoated carbides, coated carbide, cemented carbides, cermets, cubic boron, that is nitride, that is called CBN tools, and the diamond tools. These are the some of the materials. Apart from this, many materials are coming up. At the same time, many materials are invented for coating on this material. Okay. So these are all we will, some of the things we will see. The history of the cutting tool materials. If you see, the cutting tool was used during the industrial revolution, that is 1800 AD. The first tool was cast using crucible method and the slight hardened by the heat treatment method normally. So it is developed by the crucible method, and Mush found the adding of tungsten, one can increase the hardness of the tool life, that is air quenching and all those things. F.W. Taylor in Pennsylvania did the most of the basic research on metal cutting between 1880 to 1905, invented high speed steel. HSS, even nowadays also people will be using, and the carbide tool was first synthesized in 1890. This is about the history. Okay. So, 1800 AD it started, and the research on cutting tools, basic research was done up to 1905. 1880 also the tungsten carbide also synthesized. Okay. Coming to the HSS, that is high speed steel, the composition goes 18% tungsten, 4% chromium and 1% vanadium, and sorry, it is 0.6 to 0.8. Okay. This was found early 90s, very highly used for hard alloy steels, can be hardened various depth. Okay. Good wear resistance, high toughness, good for positive rake angles, and there are two basics. What I mean to say is, the best thing about this material is it is having high toughness compared to other materials. This is the toughest material because it can absorb the impact and all those things. So, from among what I am teaching is the highest toughest to a cutting tool is HSS, hardest is diamond basic. Okay. So, there are two basic type, one is molybdenum, that is M series, another one is tungsten series, that is T series. High speed steels are there. T series is same as what we have seen, that is 18:4:1, tungsten, chromium and vanadium. Okay. M series normally 2 to 10% will be molybdenum in 18% instead of 18% tungsten. Okay. So, if I am going to use 2 to 10% in 18%, so I am using another, assume that 8% I am using, 10% I am using tungsten. Okay. The chromium, vanadium, tungsten and cobalt will be the normally binder, better abrasion resistance, less expensive and less distortion, and 95% of HSS industry are M series one. Okay. So, now the question is, if we have tungsten series, that is T series, why we have to go for M series? The reason for this one is it is less expensive. Okay. This is the reason why molybdenum is M series, the molybdenum series, the molybdenum cost is low, but the properties are approximately same. So, that is why we are going for the M series. So, another one is, normally these are manufactured by casting and powder metallurgy technique. So, the applications, it can be turning tools, taps, gear cutting, drills and all those things. Okay. So, we are going for the uncoated carbides. The second variety is, most of the HSS, the basic problem is high temperature hardness is very less. That means that hot hardness at elevated temperatures or the hot hardness is low. So, if at all I want to machine a hard material where machining temperature goes high, in that circumstances the HSS will fail. Okay. So, the low life for high speed machining, normally if at all I want to go for high speed machining, in that circumstances it is very less. That is why we go for the next version, slightly higher version, that is called uncoated carbides. Uncoated carbides are uncoated cemented carbides, class of hard tool material based tungsten carbide using powder metallurgy. There are two basic types in this one. One is tungsten carbide based, that is called non-steel cutting grades, and the titanium carbide and tantalum carbide based tungsten carbide tools. These are the two varieties of cutting tools are there. First we will see the tungsten carbide. The particle sized 1 to 5 microns are press sintered into the desired shape, and percentage of cobalt may vary. Cobalt is a binder basically. Okay. So, tungsten carbide is also compounded sometimes with tantalum and improves the hot hardness. To improve the hot hardness, normally tantalum and titanium are used. Basically, these are developed by the powder metallurgy techniques, where we will use the tungsten carbide particles. Tungsten carbide particles are used and the binder is added to it, and they will do the ball mixing and all those things. Then they will do the compaction, sintering, and they will form. The normally the cobalt is a binder. So, it will, like assume that if you want to build the home, normally brick by brick we will do. So, in between we will put the cement. So, this is nothing but the cobalt, this is nothing but cobalt. and this is nothing but your tungsten carbide. Okay. This is how this will work. Okay. Next we will go for titanium carbide. Okay. So, in the titanium carbide TIC nickel molybdenum matrix will be used. This is steel grades. Normally previous one tungsten carbide which we are using is non-steel grades, where if at all we want to use the non-ferrous based, those can be used. So, titanium carbide as a base material and nickel molybdenum is the matrix is used. Good wear resistant and poor toughness. As I said, toughness is good in HSS, good for machining the steel and high speed than tungsten carbide. So, you can use for higher speed than the tungsten carbide. So, when the temperature goes up, it can stays. At the same time, it is very good for the steels. Okay. The high compressive strength, normally general properties, if you see high compressive strength but low to moderate tensile strength, this is the problem, but you have a compressive strength is very high. So, normally it will be very good. So, high hardness and good hardness, I said at elevated temperatures also it possesses its own good hardness. So, wear resistance is very good. So, it is normally do not wear at less time. So, high thermal conductivity. So, the temperature it can conduct easily. That means from the cutting edge it can conduct to the next other parts of the tool. That is the benefit of high conductivity. Elastic modulus is in this range and toughness lower than high speed steel. As I said, high speed steel will have higher toughness. Okay. We see the coated carbides. Normally coated carbide, what is the difference between coated carbide and uncoated carbide? Normally these are the coated ones. Okay. How, what is the difference? Normally if you see, this is the difference. This is the uncoated one, this is the coated one. Okay. So, you can see normally it is a gold color, normally the coating is done on this one. Okay. So, why the coating is required? Okay. Cemented carbide insert coated with one or more layers. Normally tungsten carbide tools are not good for the steel based workpieces and all those. If at all I want to use it, what people will do is TIC, TIN, that is titanium carbide and titanium nitride or ceramic Al2O3 coatings will be done. There are various techniques, that is chemical vapor deposition, physical vapor deposition, radio frequency sputtering, there is a laser coatings are there, many techniques are there. So, okay, normally this thicknesses ranges from 2.5 to 13 microns. Nowadays very good nano coatings also coming into the market. Applications normally you can use for the steels and all those things, best applied for high speeds and dynamic shock and thermal shock, and whenever the minimum if you want you can go for this coated carbide tools. Okay. Cermets, normally what is meant by the name itself says cermet means ceramic plus metal. Okay. So, ceramic will be the base material and metal will be the binder basically. Okay. The composition if you see 70% will be ceramic, that is Al2O3, and 30% will be like titanium or something as a binder they will use. Okay. So, since there is a ceramic is there, there is a metal is there, that is why these are called cermets. Okay. The properties very high temperature hardness, that is hot hardness is very high, abrasion resistance is very good and more chemical stability, because ceramics are there, ceramics are highly stable materials. So, this if the ceramics are very high stable materials, so the chemical stability will be very high and there will not be any chemical reaction and all those things. Less tendency for adhesion, so there is a less chance of built up edge, good surface finish while machining the steel and cast iron. And so, poor, only the problem here with this one is it is having poor toughness. So, if at all I want to use for intermittent cutting, it cannot be used. For intermittent cutting you need good toughness in the tool material. Okay. So, this is very good from the chemical point of view, because this is having a dominating ceramic. Okay. So, ceramic is highly stable material. The next one is cubic boron nitrate, CBN, whatever you can say it as a CBN is commonly known as next to diamond and the hardest material that below the diamond, and 0.5 to 1 mm polycrystalline cubic boron nitrates normally is high wear resistant, brittle in nature. This is the only problem, it is brittle in nature and it is very hard material. Okay. So, if it is brittle, normally intermittent is cutting is the problem, and catastrophic failure will takes place. It cannot be used for intermittent. Catastrophic failure will takes place. So, manufacturing techniques, normally powder metallurgy, these are used for the machining hardened steel high temperature, where for example, nickel based alloys and all those things. You can see how it look like. So, completely the tool insert cannot be made from this one. That is why they will make a small bit and they do the brazing operation. Okay. So, whenever we take about the brazing, see, you may get doubt that if it is brazed, the normally brazing is done at very low temperature welding process or the joining process. So, brazing came out. So, some of the local tools which we got, unfortunately these are the brazing is going, but if you purchase from the standard companies like Sandvik, Cermets and other companies, you will get a proper tools. So, what I mean to say is that the brazing normally it can sustain up to 300 degrees and all. If it go for 600, 700 degrees the cutting tool temperature, it may not sustain, but why brazing is done still is, if you see the thermal aspects of machining, the only 15% tool takes care, okay, out of which the CBN have low thermal conductivity. So, that means that the top edge of the cutting tool will only experience most of the heat and it cannot conduct towards the bottom side. So, there is a very less chance of going. If it is not maintained properly, so it will goes off. Okay. So, diamond tool also look like this only, instead of CBN they will put the diamond. So, diamond normally will be the polycrystalline diamond and single crystal diamond will be there. Normally these diamond, do not think that these are the diamond that people wear or something. This is the artificial diamonds, low friction, high wear resistance, good cutting edge, and the single crystal diamonds are used for machining copper to get high. Normally this is called diamond turning operation. Nowadays it is one of the good process, and I will teach whenever I am teaching about the advances in metal cutting processes or machining process. They are brittle, rake angle should be low. So, polycrystalline diamond, compact synthesized crystals and fused high temperature and all those things. Okay. So, this is about diamond. One thing, please note that diamond is the hardest material, HSS is the toughest tool material. Okay. So, do not confuse between the toughest tool material is not the diamond. Okay. So, it is a brittle material and it will fail in the brittle fracture. Okay. So, the comparison of various tools, if you see the cutting speeds, if the cutting speeds versus tool life, high speed steel will have very low range of cutting speeds, then the cast alloys which I have not taught, then the carbides and the ceramic, that is Cermets and all those things. Diamond will follow next, CBN followed by diamond will come. Okay.